This video will incorporate all of the details and research that went into our semester project for ME423 heat transfer. For our semester project, we wanted to analyze the effects of heat transfer that occur within a typical blow dryer. We plan to use concepts that have been discussed in class regarding heat transfer across multiple layers and boundaries. We also wanted to incorporate radiation effects from the heating coils as they begin to glow. We also wanted to include any effects that come from different types of fluid flow within the blow dryer. We began our project by taking measurements of each component of the blow dryer. Since the shape of the nozzle of the blow dryer is slightly tapered, we measured the entrance diameter and exit diameter and took an average between the two, treating the blow dryer as a cylinder. We did this for both the external casing and the internal insulating material. The internal insulation was made from a mineral called mica, which is found in insulating for typical electronic assemblies. The heating coil was made from nichrome, which is a common material for resistance wiring that has excellent corrosion properties. We also made sure to measure the diameter of the heating coil and the total length for future calculations. As air enters one end of the blow dryer, it expands due to an increase in heat and is sped up by a fan instead of the dryer. Here are our measurements for the inlet and exit velocity. We found an average velocity that will be used later in this presentation. We also measured temperatures of the surroundings, along with the temperature of the exit of the blow dryer, the temperature of the nichrome coils, and the surface temperature of the blow dryer. We took all these measurements after the blow dryer had been on for some time, reaching steady state conditions. Each temperature was attained using a thermocouple, but the temperature of the coil was found using an infrared thermometer. We found some helpful properties for the three main materials for the blow dryer in the heat transfer textbook, along with online sources. It is important to note that these values represent the emissivity of the materials, while this value represents the surface roughness. We did not need to find any emissivity of the mica, nor the surface roughness of the plastic or nichrome. Looking at a cross-section of the blow dryer, we can begin our model. Each part is represented. The mica is the gray layer next to the pink plastic. On the actual blow dryer, these two surfaces were very close to each other. This figure also includes the coils, which are wrapped in a spiral motion from the back all the way to the front of the blow dryer. As air is blown across the heating coils, it undergoes heating by convection. In order to appropriately show this effect, a resistance network is started from the center of the blower to the outer surface of the mica. We know that the resistance due to convection can be determined by taking 1 over the product of the convection coefficient and the surface area present. The cylindrical surface area of the mica will be used for this. In order to account for the radiation effects of the coils, an additional resistor was included that acts across the coils, radiating to the outer surface of the mica. This is seen in the close-up picture, showing that the radiation resistance comes from the heating coil. This resistance value is found with the radiation coefficient instead of a convection coefficient. The surface area for this radiation will be the total surface area of the heating coils, since that is where the radiation comes from. These two resistors are acting in the same control volume together, and so they must be represented in parallel. This is also shown in the figure. Expanding our model leads to two conduction resistances that are present on the outer layers of the blow dryer. The resistance network first passes through the mica insulation and then through the outer plastic boundary. These are both evaluated using the same expressions and will be included in the total resistance network. The heat flux leaving the system is represented with another resistance in parallel, which includes the convection resistance and the radiation resistance. The convection coefficient for the convection resistance will be due to free convection instead of forced convection like earlier inside the blow dryer. Each resistance that is present is now accounted for and can be combined for a total resistance. In order to fully evaluate this equation, the convection and radiation coefficients must be determined, and each property will have to be put into this formula. Starting with the internal forced convection, we find the Reynolds number reaches 58,000, meaning turbulent flow of the air as it moves through the blow dryer. Using the stiffness surface of the mica, the friction factor can be found and used for calculating the Nusselt number for the cylinder. This leads to a Nusselt correlation that will result in a convection coefficient for the internal forced convection. This value determined also correlates with table 1.1 as shown in this picture. The inner and outer radiation coefficients can be determined with the properties of the nichrome and the plastic, along with their respective temperatures shown here. On the outside of the blow dryer, it is cooled by free convection. A Raleigh's number is determined, and a Nusselt correlation leads to a convection coefficient of 5.08 watts per square meter Kelvin. This also matches with the information given in Table 1.1. With these four coefficients known, the total resistance of the network can then be determined. The conduction resistance from the mica and the plastic are represented, and each resistance is summed together for a total resistance of 0.8507 Kelvin per watts. This then leads to a total heat transfer rate on the outer surface of the blow dryer of 68.3 watts. We were able to include the effects of turbulent flow and the radiation from the coils for our project. After analyzing the results, only 68.3 watts of power was delivered to the outer surface of the blow dryer, meaning that the insulation layer of the mica performed fairly well. However, typical blow dryers are designed to maintain an outer surface temperature of about 60 degrees Celsius to prevent burns to the skin. However, the surface temperature of our blow dryer was measured at 78.8 degrees Celsius after it had reached steady state conditions. By understanding the heat transfer rate through the blow dryer, we can see that improvements could be made to future blow dryer designs. If the total heat transfer was able to be reduced to the outer surface, then the outer surface temperature would be lower to prevent harm to users. This could be achieved with a thicker insulation of mica or additional air pockets between the mica and the plastic cylinders. However, overall we are satisfied with our results and our findings and the work that we did.